All right, this is Solutions video number 2. I'm going to talk to you about properties of solutions. Now that we've had our little introduction to solutions, we can get a little more into it. So foremost, I want to start off by defining the term solubility. This is the maximum amount of solute that will dissolve in a given amount of solvent. So the maximum amount that can actually dissolve at a given temperature. It's important to bring that to your attention, and I'll elaborate here in a minute. Okay, so 3 more definitions: unsaturated, saturated, and supersaturated. I'm going to start unsaturated. I'm also going to show you a little simulation to help you understand this. Unsaturated is the solute is completely dissolved in the solvent. All right, so in an unsaturated solution, the solvent can still hold more of the solute, whereas in a saturated solution, that is the maximum amount that can be dissolved in the solvent. Okay, there would be no undissolved solid in the solution. Okay, and then the last example, this is where there's more dissolved solute than there would normally be. These are called supersaturated solutions, and they are extremely unstable, and they're often formed by raising the solvent temperature high, dissolving the solute, and then slowly bringing that back down to a lower temperature. So what I want to show you here is an example of a supersaturated solution. This is sodium acetate. And sodium acetate, once it is seeded with a little additional sodium acetate, it will begin to crystallize. Okay, it'll spontaneously begin to crystallize, which is so cool. So we're seeing the crystal lattice structure reforming, and as a result of that reformation, energy is being released. So when we get to do this one in class, you'll see in the end it's very warm because it's an exothermic process. Now let's talk about the units of solubility. All right, so we have several that I'm going to talk to you about. The one that I'm most concerned about would be molarity, and that is the moles of a solute per volume, and that volume must be in liters. All right, so if it's in milliliters or nanoliters or whatever, you have to convert it into liters. We have grams of solute over the milliliters, so that would be a mass to volume. We have grams over grams, which would be a mass to mass. And then we have parts per million, or even parts per thousand. If you've worked with the saltwater tanks in the classroom, we measure those typically to go around 35 parts per thousand. So that would be the parts of the salt to the solvent or water. Okay. So what I'm going to do here is I'm going to take you to an online PHET simulation to explore this idea of solubility, saturated and unsaturated solutions. All right, so check this out, guys. We're going to explore solubility a little bit here. I can choose from all of these compounds. I have chosen copper 2 sulfate as my solute, water as my solvent, and I also have a concentration probe here I can use to determine molarity, which is showing 0 moles per liter, which makes sense. And so now I'm going to add some of the solute to the solvent. This solution is currently unsaturated. Okay, remember, solubility is the maximum amount of solute that a solution can hold, that a solvent can hold, rather. So let me add a little bit more here. You see it's getting darker, a little bit more, and there it is. We are now saturated, so that means this solvent cannot hold any more of the solute. This is a saturated solution, but just for fun, I'm going to shake a little bit more, and you see it starting to form there at the bottom. Okay, and let me grab my probe here and check the molarity or concentration, which is 1.380 moles per liter. Okay, so I am going to add a little water and dilute this sample. Okay, and let's see if my concentration, no, it's still up there. So let me add all the way to the top, 1,000 milliliters, and we are still saturated. So what I'm going to do is remove that, get some potassium permanganate, go with a solution liquid form, and let me get rid of some of this water here. And why are you not working? Because this is the drain, Mr. Peterson. Okay, and so let me add some potassium permanganate. Beautiful. We're going to, in AP chemistry, we'll do a redox titration with this chemical. So cool. All right, so let me check the molarity out here. 0.07 molarity. Now I'm going to evaporate it, okay? And one thing I should point out is I can dump all of this in. I'm not going to saturate it because I'm already adding a solution. All right, so, but if I evaporate and remove the solvent, I can then reach that saturated stage. And if I keep going, I end up with the crystals. Okay, let me add a little bit water because I do want to check the molarity here. I'm just a little curious. So it went up to 0.480 moles per liter. So hopefully that gives you a little bit of an idea. Feel free to come check out this site on your own, but covering these ideas of solubility and saturated and unsaturated solutions. And right now I'm going to show you something really cool dealing with supersaturated solutions. All right, so here's that website again if you want to check out that simulation on your own sometime. Now, this is something, depending on the order that you viewed podcasts and that I've assigned them, because it'll vary from year to year, you may have already been introduced to these two terms when we talked about writing net ionic equations. These are the ideas of the process of dissolving. What does that include? What does that actually entail? Well, it entails both solvation and dissolution, and these two terms are often used interchangeably, so I want to make sure to make a distinction between the two. Okay, so what you see here is a sodium cation being surrounded by water. Now, more than likely, we have not yet got to our bonding unit, all right? So the way these are orienting one another is known as an ion dipole bond, okay? So we have these ion dipoles that are forming, and if this was the cation of sodium chloride, the same thing would be happening to the chloride anion, except the water molecules would orient with the hydrogen molecules surrounding, which are the little purple circles in this space filling model. Okay, so literally the process at which the solvent is surrounding the solute is solvation. In this example, this is a cation, whereas the dissolution is the process in which the solute gets dissolved in a solvent. So in this animation, you're going to see water and the crystal lattice structure of sodium chloride interact. Dissolution involves a couple conceptual steps that you need to understand or at least begin to think about. Step one, the crystal lattice structure, those coulombic attractions, those bonds between the cations and the anions are also need to be broken. It takes energy to break bonds. So there's an input of energy that goes in during that process, okay? That's an endothermic process. But the same is true with the hydrogen bonds among water. So those, in this example, water being our solvent, in that example, those bonds must also be broken. And so what happens is we have a step where the lattice structure is broken. We have a step where the water, or in this any solvent, is broken. And then we have the final step of solvation, where these ion dipole attractions, these bonds, if you will, form. And that is an exothermic. So endothermic to break the bonds of the lattice, endothermic to break the bonds of the solvent, in this case water, and then exothermic when the actual solvation occurs. So that is the entire process of a solute dissolving in a solvent to form a solution. There's actually quite a bit going on there. All right, so the last thing I want to touch on is the fact that the solubility and the rate of dissolution depend on temperature. And I alluded to that earlier. I said that temperature piece is very important, that you're given that, because it's going to change depending on the temperature. The reason for that is because as temperature goes up, kinetic energy goes up. So you may recall from physical science, all right, 1/2 mass times the velocity squared, okay? So the velocity, that speed, is what increases. And if speed is increasing, then collisions are increasing, and there's more energy and motion in the molecules. So let me take a look at 2 examples here. First one, solubility of solids. This increases as temperature increases, and it's intuitive. Okay, if I want to make hummingbird water for the hummingbirds, and I need to dissolve 1 part sugar into 4 parts water, I'm going to heat the water. Okay, if I want to supersaturate something like the sodium acetate video you saw, I'm going to need to heat the solvent so I can get more of the solute to dissolve. But the opposite is true for gases. So as the solubility of gases actually goes down as temperature goes up. And that's really cool to think about, because it leads into the idea of how those gases are actually dissolved in the water. What does it mean if they have more energy? Well, if the temperature goes up and the energy goes up, they're going to escape from that solvent and go into the environment, the atmosphere, whatever vessel they are in. Okay? Whereas for a solid, we have that interaction, that speeding up of molecules, etc., and that's going to increase solubility. Really cool. Take a look at this. Here is a solubility versus temperature graph. This is for the solids, and you can see nearly all of them are going up. But what about here? What's happening over here? If you look here, this one's not following the pattern, okay? And so the solubility is actually decreasing as temperature increases. And that's an even crazier idea to think about, because then that gets us into applications of reversible reactions, equilibrium, and Le Chatelier's principle. This particular compound is exothermic when it dissolves. So it's giving off heat. So if heat is put into the system, it actually pushes to the opposite direction. So it favors the reactants, i.e. it favors the solid. Really cool to think about. And here's a graph showing 4 different gases, and you can see as temperature increases, solubility is decreasing because the kinetic energy increases, the molecules move faster, and they're able to essentially escape from that solvent and go into the atmosphere, the environment, the vessel, whatever they happen to be in. Okay, so you do have a problem set I want you to look at for this, and we are getting to a point now where we can move into some great mathematical computations involving molarity. So I will see you guys in class.